Hi, in this mini lecture I will introduce or I will show how to implement the digital systems using multiplexers. This approach using a multiplexer is used in many programmable devices where you can change the function generated by MUXes only by changing the connections without replacing any gate from the device. Okay, so the same multiplexer can be used flexibly for generating many different functions. Let's start with well-known function, well-known system, which is can be called a voting machine. We named it this way. 3-bit voting machine, but also you know that it is a majority of ones. It can be named majority of ones detector. And from the full adder, you know also that it is a cout, simply cout output of full adder, cout of FA. Okay, these three names are describing this function, which is put in this table. And the goal is to implement not in this way as we did before, so it is a sum of two of them, all the combinations of these products are present here and added together using gates. But instead of having gates, let's assume you've got only a multiplexer, and a single one is enough to implement it. What's the approach? The algorithm, one of many, of course, it's not the only solution, is to put as many inputs as possible to address lines. You've got the same number of address lines in this case of multiplexer as there are in the truth table. So you put it in the same manner, starting from A as a most significant bit. It is the simplest way. B in the middle and C is LSB, so least significant bit. And then from the operation, principle of operation of the multiplexer, you know that if you put 0, 0, 0, it is the first row of this, you simply select this input, and this input's value is transferred to the output, Y. And the value should be 0, as it is stated in this table. So you must put 0 to be transferred on the Y, and Y in this case is 0. And by changing to the next value, 001, you simply read the value from table and put 0 also here. So you simply copy the truth table values into the appropriate inputs of the multiplexer. And earlier you connect variables, inputs, to the select lines of the multiplexer. It is the simplest solution of it. And now you have implemented majority of ones detector using, or cout, using a single multiplexer and no more elements. Let's do the same with smaller one, because this one has a lot of gates, and our task is to save the costs. So now we assume that there are only 4 data inputs and 2 select lines and 1 output. We denote it, let's start with 0 as before. You can do this in this order or in the opposite order, doesn't matter. 0, 1, 2, 3, and 1, 0 on the select lines. And now it is not straightforward solution, so you have only 4 inputs, and here you've got 8. You even have here 2 out of 3 inputs. So how to connect this multiplexer to get Y, the same function. And also, this is one of the possible solutions. And the first step, the intermediate step in designing is to construct a different version of truth table. It is a rectangular one, and you have A and B put in columns and C in rows. And you don't use gray code. It is a normal truth table. It is not the K-map. It is not the K-map. All right. By doing this in this manner, where A and B are in columns, you simply assumed that A and B will be connected appropriately to select lines. A on the left-hand side on the higher bit, and B on the right-hand side, the lower bit, 0 bit, of the select line. So A and B are put here, and that's why we constructed this in this manner. Then you simply copy the values of y's and put them into the table. So 0 here, 0 here, 0 here, 1 here, 0, 1, 1, 1. It is a kind of truth table. And then, because A and B are connected to select lines, so in the columns you've got 0 input selected, input 1 selected, input 2 selected, and input 3 selected. 4 columns correspond to 4 inputs of the multiplexer. And looking at the values you must obtain on the output, you decide what to put on the corresponding, on the given data input. So here, if you select A0, B0, so you select this input, you have 0 independent of C. Independently of C, you must have 0, so you simply static 0, you put static 0 signal. So ground can be, you can ground it. Next column tells you that for A0, B1, so if you select input 1, A and B, select input 1, you've got 0 for C0, 1 for C1. So it follows, yes, this should follow C. So that's why we put the variable from outside world. So not static signal, but it can change. It is the third input of the voting machine, of the majority of once detected. All right, so the same is here. So it is a C, 0, and 1 here. So here we must short circuit the two inputs and connect to C, and here you must put 1. It is the same as plus 5 volts static voltage, okay, high voltage. And that's it. It is also the same, but as you can see, the multiplexer is very small comparing here. Yeah? Yes, you can compare inside of the multiplexer in the lab. You will be constructed the multiplexers, and you can compare what's the cost factor of this realization and what's the cost factor of realization of this kind of multiplexer. So we have saved much by switching to the smaller ones. Okay, so the third case will be how to implement the same function using the smallest possible multiplexer, having only a single select line, okay, and two inputs and two data inputs denoted by 1, 0 to show indexes, and y should be the majority of ones or C out, and so on. And the question is how to do it exactly in the same way as before. So you must select one of the 3 inputs and put it to the other lines, select line, and this must be put in the tables in her columns, okay? All the variables which we decided to be connected to the select lines must be put in the same order in the columns of this intermediate table. The remaining ones must be put in rows. The remaining are B and C. So the shape is different. Yes, it is a rather vertical, not horizontal table, having more rows than columns. And as before, you are using binary, not gray code, binary code, 0, 1 for A, and these sequences for BC. And similarly, you put the output values, Y values inside, into this table. So majority of ones, no majority, no majority, no majority, there is a majority, no, yes, yes, and yes. Okay, this is the well-known truth tables and how we do it and how we continue, what to put, what to connect to these lines. Look, 0, A equal to 0, select this input. And you've got the values that must be obtained for the different values of BC. Values of Y depend on the BC, two variables, B and C, two signals, two input signals. And what's the function here? I can see, I recognize it. It is simply B times C. It is AND operation. So Y should be equal, in this case, when A is equal to 0, this should be equal to B times C. So you must put gate. Apart from multiplexer, in some situation, if you use a very small multiplexer, you have to use additional gates. And to this gate, you simply, it is not NAND, it is dot, okay? It is not NAND gate, it is AND gate, all right. And in the second row, for A equal to, second column, for A equal to 1, you've got, what's the function? It is OR. And this is AND. So you need another gate, which is OR gate. And you connect the output of this gate to the input here, 1 of the multiplexer. And you must connect the same signals, B and C, to the inputs of this gate. And that's it. It's a little bit less gates than you use when you implement the system in the well-known, already known way. Okay, so here the cost factor of the gates are how many inputs? 1, 2, 3, 4, 5, 6 plus 3, 9, and how many gates? 1, 2, 3, 4. And if you calculate the cost only for these two gates, you got 2 times less. But of course, you must use gates to implement a multiplexer. Okay, so you can compare the cost by yourself. Thank you.